When the atoms in a covalent bond have different electronegativities, the electrons are shared unequally and the bond is polar. Depending on the molecular shape, polar bonds can give rise to a polar molecule, one with an overall uneven distribution of electron charge. We can see this charge imbalance when the molecules are placed in an electric field. Polarity is a key feature of a molecule because it can influence physical, chemical, and even biological properties. For a diatomic molecule, a polar bond must lead to a polar molecule. Consider hydrogen fluoride, shown here as the Lewis structure changes to a ball and stick model enclosed within the space-filling shape. Note the polar arrows and the colors. If red indicates high electron density and blue indicates low, you can see that the F end of the molecule is much more negative than the H end, and thus HF is highly polar. Between two electric plates with the field off, the molecules lie every which way. With the field on, however, they become oriented with their negative ends facing the positive plate and their positive ends facing the negative plate. If a molecule has more than two atoms, its shape can affect the polarity in a crucial way. For example, in carbon dioxide, since oxygen is more electronegative than carbon, each bond is highly polar. But the linear molecular shape makes the bond polarities cancel each other, so the CO2 molecule is non-polar. Notice that the orientation of the molecules is random, whether the field is off or on. The situation is very different for water. As in CO2, the highly electronegative oxygen pulls electron density towards itself, so each bond is polar. But the V shape of the molecule allows the bond polarities to reinforce each other, so water is highly polar, as the large polar arrow shows. With the field off, the molecules are oriented randomly, but with it on, their poles become oriented toward the oppositely charged plates. The case of boron trifluoride is similar to that of CO2. Because the three highly polar bonds point to the corners of an equilateral triangle, the bond polarities cancel each other, and BF3 is nonpolar. The molecules are oriented randomly with the field off or on. Like BF3, ammonia has 4 atoms and 3 polar bonds, but the trigonal pyramidal shape means that the bond polarities reinforce each other. Thus, ammonia is highly polar for the same reason that water is. Sometimes two molecules have similar overall shapes, but their slightly different compositions lead to very different polarities. Carbon tetrachloride has 4 polar carbon-chlorine bonds that point to the corners of a tetrahedron, so they cancel each other and give a nonpolar molecule. Substituting a hydrogen for one of the chlorines gives chloroform, another tetrahedral molecule. But now the polar bonds reinforce each other. As a result, chloroform is highly polar. There are even cases when two molecules have similar shapes and identical compositions, but different polarities. Compounds such as cis and trans-dichloroethylene behave this way. Both have the formula C2H2Cl2, and both have trigonal planar shapes around the 2 carbon atoms. Yet, the trans compound is non-polar because the carbon-chlorine bond polarities cancel each other, while the cis compound is highly polar because they reinforce each other. Since greater polarity leads to stronger attractions among the molecules, the cis compound boils over 18 degrees higher than the trans compound.